morning is Deborah Lewis from University of California at Santa Cruz. And she's going to talk to us some very interesting stuff. Right? So there you go. Coming? Allegro ma non troppo. From music. Okay, go ahead.
Okay, let's see. We have pointer, we have sound. I definitely need the microphone because I'm not good at things. So let's move this forward. So a little bit of apology, big apology, no new geometry. What I want to talk about certainly uses a lot of the geometric mechanics aspects of optimal control, but using pretty much the vanilla things and mostly focused on making some choices of the actual nuts and bolts functions that go, can be plugged into that and the effects that some of those choices have on the modeling the problem. And I'm particularly kind of interested in a very, naive amateur way, biomechanical systems, and so looking for optimal control problems where I think a key point to make is not just, okay, is it possible? Is there some sort of solution? But trying to, with some notion of really finding an optimal one that's saying, choose your cost function and just really push things all the way through. Okay, and key thing is going to be bounded admissible control regions. And what happens is you get close to the boundaries of those regions. Penalty functions are often used in engineering contexts to say, don't actually hit the boundary. I'll talk a little bit about situations where you actually move on and off. So the talk yesterday morning, situations where you spend all of your time on the boundary and questions of how politely do you move around on the boundary. For some of these problems, you can start in the interior, hit the boundary, and you have issues with your functions aren't necessarily differentiable at those transition points. Purely, it may sound a little cutesy, but I want to say I don't want to think in terms of penalty, mostly because how do you decide how harsh a punishment you administer for trying to violate, okay, you're crossing that line, bad system, naughty system. So I find it easier to say, okay, think of it in terms of give an incentive for cooperation. You're going to bribe the system not to push that envelope of the control region that hard. And, okay, what's the distinction? I'll make a little bit of a pitch for me that's saying, okay, I do have a sense of what I decide to do with an incentive when someone stops doing what I want. You stop giving them, you don't reward them. So I'm going to look at a situation where my penalty is required to go to 0 on the boundary of the admissible control region. And so I'm actually subtracting a little bit from the cost. And you need to be a little bit careful that you don't have a negative cost. Otherwise, you say, well, let's spend eternity hanging out collecting negative cost. Oh, system, wake up. Hello? This is nature's way of saying spending too much time on one slide. Okay, so I'm going to look at situations where I'll have parameterized families of incentives and try to have those parameters model some sort of personality or context dependent aspects of the situation. So here, what I'm going to call a moderation incentive is simply, I want it at least to be a continuous function. A lot of the ones I'm looking at will be smooth so that my calculus works nicely. And really the only main requirement is I want that function to go to 0 on the boundary of the admissible control region. And those regions will typically be varying in size depending on the state value at the given time. Most of the examples I'm looking at will be what would fall into this monotonic heading, that my control regions are level sets of some function, and I want this incentive to be something that drops off in a way that's consistent with that level set structure. So here's just a very quick little example, a little bit of a sales pitch that throwing in these parameters will actually get some differences in behavior. If you don't like the attack defense, think shooting baskets, lying on your back, launching the ball up in the air. So you have a unspecified starting position. This is all happening on the line. You're trying to launch some sort of projectile to hit a target, and it's specified the initial vertical launch. Other than that, the starting position is free to vary. You have controlled velocity. So let's see what happens so I'm going to look at a family of cost functions. Here, tau is just either 0 or 1. They only differ by a constant term. So big thing I want to emphasize, which for me as a Hamiltonian person, same evolution equations. So saying, oh, shift your Hamiltonian by a constant, if you're kind of going, that doesn't change anything. It does not change the dynamics, but it does change if you have a system where you don't specify the duration of the maneuver. Then there will be Pontryagin's maximum principle will say your Hamiltonian has to equal 0. And so that constant will shift the starting data, if you will. So here we have that term little c over x squared 2. That's going to be measuring the cost of the risk from it. This target's defended. And how heavily it's defended depends on how close you are to the target. The mu term looking like a kinetic energy, that's cost of control investment. How much effort is it taking to push this projectile around? And then the constant term is simply going to adjust, does it satisfy that property I'm interested in of that the control-dependent cost has a correction term that goes to 0 on the boundary of the control region. Here my control region is admissible controls are just a unit ball for all of those. For any of these parameters, the optimal solutions follow segments of an ellipse. So what you're adjusting is where the center of that ellipse is to get your starting point and that you actually hit your target. So if tau is equal to 0, let me put that back there for a second. So if it looks like just kinetic plus potential energy, then all of your solutions will follow arcs of a circle. Those parameters aren't buying you any flexibility in the shape of the trajectory. They'll control how fast you move, but then it's only the ratio of that. So little c is the parameter scaling intensity of defense of the target. Mu is capturing some sort of mellowness, moderation of whoever's steering the projectile. And so in that situation, kinetic plus potential, we like that kind of Hamiltonian. It's not really a two-parameter problem in any meaningful sense. Your mellowness just adjusts your perception of how threatened you are. The other situation where you would throw in that constant that has the control cost going to 0 on the boundary of the penalty, as it were, going to 0, then it depends non-trivially on both those parameters. You start seeing that as you play them off against each other, you follow different paths. And so here, if I can control my pointer, just have some sample ones here. These gray curves are actually the arcs of circles. So those are the paths that would be followed if you just have the straight kinetic plus potential. And also then there's some limitations on, again, that you don't want to allow negative cost. So the most moderate parameter allowed then gives you the same paths but possibly different speeds. If you are less moderate, you're more aggressive, then you start in closer and blast in fast. So the range of strategies are, if you're very mellow, moderate, maybe very experienced, aiming at these things, you start way back and do a lot of your vertical climb out of the really dangerous range, and then come in fairly quickly, more or less horizontally. Depending on how far out you start, this starts. So a mellow strategy is start far away, do some climbing before you get into the really risky area. An aggressive strategy is start close and blast more or less straight up at the target. Okay, so, come on. Okay. Now, I'm not interested in shooting projectiles at targets, so this is just a pet obsession of mine, no pun intended. But an interesting, I'd say, control biomechanical system. The distal forelimb of a horse is this corresponds to our wrist, hand, middle finger. So current research suggests these very long, lightweight limbs are not for rapidly fleeing predators. They're for ambling along, snacking, so that living in a very arid terrain, you don't burn up more calories getting from point A to point B than you gain eating. So this whole very, very lightweight structure, really neat, from an engineering perspective, really, really nice energy recapture system, all these tendons, as the weight comes in. They're large animals, and so making efficient use of the amount of energy it takes to move that much mass forward, this seems to be what nature was pushing towards. And people just said, great, cool, they exist. We can make them do all kinds of really bizarre things. So, horse racing, cutting may be an entirely American sport, but just sort of looking at, imagine the forces being imposed on those legs. I mean, these are probably roughly 1,000-pound horses. These maybe, boy, I should shift, maybe 450 to 500K, a little bit lighter weight. Incredible forces being exerted on landing on some of these sharp turns. How is it that a limb that was optimized for really energy, it's like taking a Prius and doing the most bizarre, outrageous stunt driving you can think of, only much more so. So that they can do this, a sensible horse in nature would maybe do any one of these moves a couple times in its lifetime. And they're being asked to do that dozens of times, very extensive, on a daily basis if they're being used for these sports. How do these limbs survive? How does the motion of the limb adapt to going from hours and hours of very low key, energy efficient? So the ambling around would be, okay, you want to be energy efficient. These are mimicking natural behaviors. You want to survive. And so how you can think of a continuum of responses that capture those. And then here's some ones that, as far as I know, this is not anything that they would do by choice. And you can get a measure of how artificial by just how mechanically manipulated the limbs are to get them to move their bodies in that way. Here, imagine playing football wearing a cycling shoe. These, again, and all sorts of other things going on, very artificial, incredibly, incredibly destructive of the limbs. And also fair amount of deliberate infliction of pain and the pain response. So this is a very high knee lift. You can't see it here, but there's chains around those ankles. Caustics have been applied to the ankle beforehand. So imagine the worst if you've ever had a skin infection, and then someone wraps a metal chain around and says, shake your hand all the time. So pain, manipulation of forces applied. And for someone modeling things, I don't need to get approval or funding to run experiments. I just need to go to YouTube and get video. What I do need to do is get efficient at capturing the video and extracting points. But in all seriousness, the people that do these kinds of, this is the Olympics, this is their world championship, this I think is also world championship. There's a lot of actual experimentation that's been done. And so I have a pool of experimental data to test out some of these things once I can get these models up and running. But the horse is not the official mammal of optimal control. The cat is the designated, if you're talking about optimal control of living things, you talk about cats. So this is joint work with Peter Ulver that's been dragging on for forever. I call it the scaredy cat of key thing that I want to bring to this model. Wonderful work has been done on the problem of, I'm not going to say falling cat, and then just go oops and fall. It was held upside down and dropped. Okay, but the effect of psychological factors is the key thing we want to bring into this problem. And we were first thinking about, well, we'll use this to test out some geometric integration schemes we were working with. And initially kind of joking around and conversation by conversation, like, no, this really is, even if you have a very, very rough, we work with very, very primitive physical model, that animal is scared. And I'll show you some more detail. These are from 1894, some of the first reasonably good high-speed photography to capture this movement. But if you see, even here, if you're into cats, and we'll see that is not a happy cat for the first part of the maneuver. Okay, and so we want to then say, what happens if you introduce the effect of its state of mind while it's going through that? So a little bit of a timeline, 1894. Mary was able to, I can't pronounce that properly, pardon my French, was able to capture that many frames of the cat doing this maneuver. He also photographed something that looked like a whippet, rabbits, various other animals doing this flip. Rabbit actually does a really good job with it. It's got massive hindquarters help. But it was purely a qualitative and very, very brief summary. The strategy seems to be split it into everybody that I know who's modeled this, splits the cat roughly into a front half and a back half. His qualitative description is sort of the trick of turning over with zero angular momentum is everybody knows, okay, you have to somehow counter-rotate, but that they can do it so quickly involves you change the relative angular momentum of the limbs by splaying out the limbs in the half of your body that you want to move relatively slowly. And then here, I brought my little, not a cat because my stuffed cat takes up too much space in my luggage and it doesn't actually twist that well, that if it splays out, say, the back half and then tucks in, this is a little stuffed iguana, tucks in the front half, then as it counter-rotates, the back half will have relatively small angular velocity relative to this. So you can turn the front half fairly quickly while this isn't doing that much of a turn. And then once the head's, it seems to matter a lot to the cat when it can start seeing the ground. It knows how much fine-tuning it needs to do. And then it reverses that and splays out the front end, streamlines the back half to whip the back end around. So that's a qualitative study, but no equations in his work in the late 60s, Tom Kane, and I have to admit I don't know Cher's first name, came up with, by an incredibly bizarre process, a system of ODEs that modeled the drop cat as two rigid bodies coupled with a no-twist joint. So actual ODEs, very, very idiosyncratic derivation of that system. And then in 1993, so almost 100 years after Mary's work, Richard Montgomery came up with an absolutely beautiful, crystal clear, optimal control, very geometric model of the falling cat that then showed that, in fact, their characterization actually does make sense. Whoops, let me back up a second. I didn't want to do that all right. There we go. So really, really found all the geometry in the problem and put the system in a context where it fit as a beautiful example. And I think this is probably the most elegant, most streamlined, as it were, example of how this orientation change can be done with zero angular momentum. And my only real criticism of that is, and correct me if I'm mistaken, it's geodesics you think of as, okay, you're optimizing kinetic, minimizing kinetic energy investment, and I don't think that was really the cat's top priority. I think it was scared. So this is sort of my translation of cat facial expression. Again, some of these, if you look, that ears flattened out is, at least in my experience, when we meet again, you're going to regret having done this to me. And this is a much lower concern, but it does affect things. I'll show you in the next slide or two where this is heading. Cats can, in fact, twist. The no-twist condition it simplifies, again, if you want really tidy dynamics and your goal is to say, what is the simplest system that can still do this thing, then the no-twist condition, I think, is a really nice effect. But cats, key thing, they don't have collarbones. I will again use my little stuffed model here. We stand upright. We have collarbones that stabilize. Our shoulder blades are aligned this way, so we don't flop all over the place when we try and walk around on our hind legs. Quadrupeds typically don't have collarbones. Their shoulder blades run down at a fairly steep angle to each other, and so they have typically, even a horse, which is not a very flexible animal, has a fair amount of that kind of twisting flexibility, and that does change. So here, and that's a little side. This was very, very good at his PR. That this article in Life magazine actually appeared before the scientific article on this research. I think this was an era in which anything relating to space was extremely marketable in the US. So I think part of what was going on in their model is, they were using the cat as inspiration, but they were getting funding to develop maneuvers for, there's now, what's the movie Gravity with all that, how does somebody move in zero gravity? And so they were taking the cat as sort of a role model, but this column is the one that was actually, I would say, their final target. And in fact, if you look at, so here, this set of images is taken directly from their scientific paper. They had some photographs, had their equations, had some parameters, tuned the parameters. And something to notice here is this one, so the little crosses are trying to match where the limbs are, and already by this one, the model predicts having the one forepaw coming pretty much out of the center of the cat's chest. Here again, those X's for that. So this would say the cat's front part of its belly is pointing out here. And in fact, the cat's already, the forepart's facing straight down. Now, if you there was a picture that didn't have the cats in it, superpose it on that image from the Life article, notice those X's, like particularly this one. I would be willing to bet non-trivial money that this is a situation they actually match their parameters to. That even though they're superposing on a cat, that some of their conditions were set to match the relatively limited flexibility, even of a gymnast, of a human being. You're just getting much, much better. Again, if you look here, he's facing straight out while the cat's already almost looking down. Okay, so that's, again, the psychological impact is the main thing we're after, but to say, how much can you relax some of those conditions without getting a nightmarishly, for my standards, something that still is tidy enough to count as geometric integration, but a little bit closer to what I'd say is the reality for a cat. So I will not spend a bunch of time on the details of things. So the context that I'm looking at is fairly restrictive. It's what's called affine controlled systems. So have the drift field, I'm trying to remember my official jargon, and then some vector fields that are scaled by the control parameters. And then I'm going to use some family state dependent and interested in, when it really depends non-trivially on the current state of the system, carve out a level set to be the boundary of my miscible control region, and just for simplicity, having that be that it's going to be like an ellipsoidal control region. There's no conceptual reason for this. It's just computationally convenient, and at this point, I need all the computational convenience I can get. Okay, and so here then, this is just chasing through how to set up the machinery for building the cost function, in particular moving towards the Hamiltonian system that Pontryagin says will give me, and I want to make a clear distinction between what I'm going to follow Pontryagin language and call the synthesis problem, so finding solutions of that Hamiltonian system versus knowing for sure I have a truly optimal solution. Okay, on these examples, I'm not going through and explicitly checking that I really do have a minimum. I just have, I have a critical point, and focusing on situations where, I have an explicit formula for how to take, build some linear maps out of these vector fields, flip things across, taking various adjoints, and that the optimality is always going to just be a rescaling. Okay, so the direction that the control is pointing is cut and dried, and what I'm after is that my cost functions are going to tell me, what speed is that happening with. Okay, and boy, don't pay a ton of, pretty much take with this slide, for certain situations I have explicit formulas for how to do some of this stuff. What those formulas look like, don't worry about that. And the only structural thing to look for here, since I'm looking at control regions that are unit balls with respect to a non-standard norm, I'm going to take my cost functions to be, take some appropriate power of that quadratic form's evaluation on my control, subtract that from 1, so when I hit the boundary, this will be 0, and then I'm going to take powers and do some rescaling. Here's my moderation function, and I'm typically going to be interested in what happens when I choose this A. So this cost correction, that incentive for good behavior, is always finite. It never hits 0. It's finite inside. Its derivative can be infinite. And in fact, so situations where I choose alpha such that this has infinite derivative, that's to say you're never, ever actually going to hit that boundary. And choosing P and alpha is going to determine the shape of that curve as I get close to it, and just how averse my system is to getting close, and how rapidly that aversion starts getting fairly powerful. For these situations where alpha is actually strictly between 0 and 1, they may not be the prettiest formulas in the world, but they are explicit formulas. Things can be neatly expressed in terms of the ratio of this is built out of the evaluation of that, given your auxiliary variable. So what would be the fiber information in your cotangent bundle, flip that across into the vector space that your controls live in, apply the quadratic form, rescale by that moderation function. And then that gets plugged into various explicit formulas. Now, if you take alpha all the way out to 1, then it's the minimum of something. You can actually hit the boundary, and so you have to say, okay, well, if you're in the interior, you have this expression. Once you hit the boundary, then you just have to say, okay, I've hit that wall. I can't go back. Come on. And so here, it's a minimum of these two things. We'll have the analytic complication that when I'm using those kinds of cost functions, I will typically lose differentiability and only have continuity of various things. And if I have a system where I could be moving on and off this boundary, that switching aspect is something that personally, if somebody's good with managing switching, I would love to talk to you about it, because it sends me around the bend trying to track how many times I move on and off that boundary. And that loss of differentiability is also not my favorite thing. So here's just some sample plots. You can see that you can control, depending on how you tune those parameters, how sharp the dogleg is. So, and then this is probably the more realistic comparison, even though it gets a little more spaghetti-like, of rescaling things so that when your control is 0, you just have that moderation function. But so I'd say take-home thing from here is that by tuning those parameters, you can adjust the speed of reaction to, okay, just how quickly, so say for this one, That's if you want to be almost on the boundary. You can think of that as being just take a bang-bang approach and just smooth it a little bit. Now, how that works numerically, that I need to figure out. But as far as analytic things, this, as you push this parameter, can be just, okay, replace a discontinuous bang-bang optimal approach with a ever so slightly smoothed out with it. With the streetcar problem yesterday, any streetcar driver who actually did a bang-bang implementation would be in a different line of work pretty quickly. It's hard on the passengers, it's hard on the vehicle. So trading off damage done to the system by doing something very rapidly against the pressure to do things rapidly, having these different choices will hopefully give some flexibility. A special case, which is where I think all the examples I've done have been focusing on this, I think has a little bit of a geometric interpretation, is a case where 1 over alpha, so 1 over alpha equal p, some nice things happen. You're getting LP norms coming in, and where p is 2, then that optimal rescaling gives you can think about just visually black solid arrow, that's the unrescaled, just the right direction for the control. Just take your auxiliary variables, flip them across so that they're living in the control space. Now, then lift that up to control moderation space. And you have a vector here. Then project that vector standard, that's renormalize, onto the unit sphere in control moderation space. And then take that rescaled vector and project it down to control space. Okay, so the more moderate, the higher you are. So you're going to push things back a little bit. But I think this, again, has some things I'm hoping to understand a little bit better. But certainly tidy arithmetic seems so far to be numerically kind of sort of well behaved. And then to relate this to some very common control cost terms, alpha equal 1, p equals 2. And now alpha equals 1 is that you can definitely hit the boundary. And as far as I can tell, you usually do slam into the boundary. This is what looks like that kinetic energy style incentive. So if you're using something, let's say, well, let's have it look, for lack of a better choice, let's have it look like a standard canonical Hamiltonian system. If your system is such that you're likely to hit that control boundary, you may be paying an analytic price for that familiarity. The engineering style logarithmic penalty function, if you take the limit as alpha goes to 0, that cost function itself is not well defined, but the rescaling it determines is a rescaling you'd get by using a logarithmic penalty. So you can think about alpha ranges between 0 and 1. Alpha equals 0 looks a lot like a logarithmic penalty. The engineering style, alpha equals 1 looks a lot like a kinetic energy, coming from a classic Hamiltonian background style choice. So, and the ones in between are some sort of continuum of responses. Let's see how I'm doing in time. So I will go quickly on some of these parts. So I will be using Pontryagin. Again, the synthesis problem is build a Hamiltonian, and in the manifold setting, then it'll be canonical Hamiltonian system, and optimal solutions must be solutions of that Hamiltonian problem. You can have solutions of the Hamiltonian problem that are not optimal, but if you're into Hamiltonian mechanics, this gives you a good handhold on how to find these things. Okay, and it's a Hamiltonian system. That time-dependent Hamiltonian will, surprise, surprise, be preserved along solutions. Key thing, if you're interested in arbitrary duration, and I think it's fair to say by far the most common, most popular, as it were, arbitrary duration problem is time minimization, where your cost function is just the clock's running. Okay, and that was, again, the streetcar example yesterday. But it doesn't need to be that. You can have situation-dependent, state-dependent, state-control-dependent systems where the time is not specified in advance. Okay? In that situation, it's crucial that your Hamiltonian needs to equal 0. So again, that if you fix the time, it's a Hamiltonian. It's going to be constant, but there's no constraint on the exact value it takes. So if you're kind of going, why is she caring about it being 0 on the boundary? How can that possibly affect things? It affects things through this condition. Okay, that once you've chosen your initial data, the evolution isn't going to be affected by a change of constant, but the initial data that will satisfy this is very blatantly affected by shifting your Hamiltonian by a constant. And key thing, there are necessary conditions for optimality, not sufficient. It gives you a machine for looking for these things. And so this just solve the Hamiltonian system, satisfy the boundary conditions, no guarantees that it really is optimal is then, well, I'll talk about the synthesis problem, if I can pronounce this. and do a quick run through of a little teeny tiny example, and I was switching variable names. So if you're going, where did lambda come from? It came from an earlier version of the slides. So this is now the streetcar problem. I didn't know it usually went by that name, but same thing, start at rest, stop at rest. I'm going to bound the acceleration, which is my control, can't exceed 1. Very simple Hamiltonian. You get your Hamiltonian dynamics, and then your control is linked in by the condition that either you're on the boundary or you have a critical point with respect to varying that control. The time minimization, again, is a very well-known one. That condition forces both those auxiliary variables to be dead zero. Your Hamiltonian's not equal to 0. So you cannot, for this time minimization, constant control cost, you're not going to find an optimal solution on the interior. It's got to lie on the boundary, and you have the bang-bang. And here you have the switching problem of you have to move around on the boundary. So if your boundary has disjoint components, tracking which component you're in can be, for me at least, a nuisance. Okay, so that's straight time minimization. Here's now the kinetic energy style control cost term. Chase through that. This one, there's no optimal trajectory. This will allow you to have some solution to the Hamiltonian system on the interior, but your Hamiltonian, again, it's not going to equal 0, because the only way that can happen is if this parameter is 0, which, again, will just force it to sit there. Okay? And if you chase through and actually compute the total cost, it's a decreasing function of time. So the slower you go, the less it costs. Yes, the slower the better. This is a Santa Cruz approach to things. Just go as slow as possible. And that just doesn't work in practice. So again, here, key thing, the constants really do matter. If I shift that Hamilton, so if I add a positive constant to my cost, I then shift things, and I can then say, okay, I can find a non-zero value of that parameter to get a 0 value of the Hamiltonian, and then getting that parameter value, then I solve for the duration of the problem. And, okay, the constraint that I can't have acceleration of magnitude greater than 1 is going to set a lower bound on just how quickly I can do this. Hopefully plausible, and hence that will then set some restrictions on the range of values that constant can have. And so the smaller that constant, the longer the duration. And so in that limiting situation where the constant is 0, taking eternity to get this job done is trying to be optimal. So let's see. I'm taking eternity to get this talk done. So this part, again, I don't think, let's just go ahead and jump over that, other than, again, being by nature and very much a Hamiltonian person, situations where you have a feedback situation where you can find a potential that's going to then encode that control. So I don't need to explicitly solve that search for the optimal control. It will just be given by compute the gradient of some appropriate function. I like that situation. If you have a moderation incentive, there's a way of building a function that depends only on the augmented information. If various conditions are satisfied, then that function, and I'll show in the next slide, will enable you to build a Hamiltonian that takes care of finding the optimal control. Only thing I want to say here to show this is, okay, so say if you have situations where you never actually touch the boundary control regions, it's kind of a no-brainer. It's just basic calculus. However, if you can be hitting that boundary, in particular, if those regions are changing with your state information, then it's not entirely trivial to verify that you can actually find this potential type function. Okay, so and that's, for me, part of the push to say, look at situations where I can control, meta-control how rapidly I approach the boundary, but I would just as soon not actually hit it, because analytically things just get messier if that can happen. And so if you can find such a function, then the Hamiltonian, so this chi term is then capturing the dependence on the control, and then this is simply capturing the state cost part of the function, and you then have a nice classic Hamiltonian system on a cotangent bundle, and you just need to worry about tuning the various parameters, tuning your initial data, so that you actually satisfy your boundary data. Okay, let's see. So for that one family where alpha is actually strictly in between 0 and 1, get nice, simple formula for that cost correction, the incentive, relatively simple, explicit expression for how to compute that function chi. If you're allowed to, so in that situation that includes the kinetic energy style function, you have if statements in there. So it's continuous. This function is now will be C1, because its derivative is then going to give you the control, which has to be continuous, but it does have that issue of the rules for how you compute it changes once you hit the boundary. And this one, again, just to stay a little bit on time, again, time relevant. For this situation and a few other ones, you can do a rescaling. Don't read. Let me just talk about this for a second. You can do a rescaling so it then actually looks like a problem where you don't have the restriction in the control region. You do some rescaling. Basically, not quite the time is money, but time is cost. Okay. And that rescaling, as far as conceptually, it brings things back into familiar context. Computationally, I am still definitely flailing around with, is that advantageous or not? Is that rescaling, that change of variables? So you rescale so that your time, time flies when you're having fun. Time, a minute can seem like an eternity when you're not having a good time. It's sort of lurking in the background of that the variation of that function becomes your new time parameter. But I don't want to say, oh, this is a good thing to do until I have a lot more experience with what happens when you run it past the computer. Okay. So then, you have then a new here then, so you can make, for any of that family, you can make it look like a kinetic, then your negative potential canonical system. So I'm going to come back to the cat before I run out of time. So I'll be cutesy about this. So what are the differences? Now get in a little bit more into the modeling of what Peter Oliver and I are trying to come up with of a cat that has some personality to it. The physical model for now is a very, very slight generalization of the Kane-Share-Montgomery model. It's still two axisymmetric rigid bodies. And the only plots I'm going to show you will be a version with the no-twist condition, but in general we'll say it's not a strict no-twist condition. There will be a term in the cost function that says, you can twist some, but it's going to hurt. Okay, and then you can twist them in all directions, and playing off, so sort of think intuitively, fear, that's going to be, again, key thing will be the psychological, it matters a lot which direction is up. Okay, and so there'll be a term that captures, how does the orientation depend, how does the orientation affect the control strategy? Payne tutors a little story about throwing his back out. Pain really changes the way you move, and your idea of what's a good strategy for getting around and performing various tasks is very strongly influenced by discomfort. So one of the things you can tune, and here being very naive, if anyone has some suggestions on good functions to use for that, discomfort associated to your actual position, exertion, control utilization. Again, for those of us who've been coming to something for a while, it's also not just how much you bend, but how rapidly you bend affects how that whole experience goes. So then this would be the control-dependent term. The control will be the velocity of relative motion, the two halves of the body. So both of these in real life can cause serious discomfort, but they're two different terms in the cost function. Key thing, the physics will be assumed to be equivariant with respect to spatial rotations. So in practice, that means doing sit-ups, doing a crunch is no more work for it than folding this way, which for some of us is an extreme idealism. I can tell the difference on that. But so that assumption means the effort involved in bending, changing shape, is not dependent on the body's current orientation. And that's, come back. And that's what's going to give then, crucially, conservation of spatial angular momentum, which is, again, the key conundrum with the cat problem is, how can it change orientation if it has zero angular momentum? And so I'm going to keep that the physical animal has zero angular, well, we'll set up the model it can have, but it has constant spatial angular momentum. Something we want to move towards is, I'd say our dream goal is to get to a mathematical model, geometrically sound, not too messy, that captures the qualitative features of Mary's description from 1894. And that will include being able to change the moments of inertia, but we are not there yet. Okay. Key thing, the psychological symmetries, very different from the physical symmetries. It has a special direction. It cares about this is up, this is down. Gravity matters to the cat. Okay, so I'm going to use crucially that spatial angular momentum, which physically, that relies on an invariance, but the control problem will have less symmetry. Okay, And so I'm going to consider cost functions where, so rho is going to be the relative orientation of the two halves of the body. Sorry, I got these slides a little bit out of order as far as notation. Gamma will then be which appears to be the upward direction to the cat in its current orientation, and actually do a, if you want to think of it as a Poisson reduction and get a system in terms of gamma and rho. Two things, again, going a little bit away from the standard canon on this, so a little heretical. My experience landing, tumbling, if you have a horse, you usually get to experience this at some point in your life of what it's like to hit the ground not properly positioned, and you stumble, and it's easy to strain things. So we'll care about the velocities on landing, not just the orientation, not just the position. And also, if you look at the photos of the cats, they typically have an extremely, they're whatever position the person who was holding them held them in when they let go. When they land, this one can't extend its legs, but they're typically very arched, very elongated. So we decide, again, we are not going to keep the traditional assumption that it returns to its original shape. But we will want it to return to the symmetries of the original shape. So that will require that the two halves, their axes of symmetry, lie in a common vertical plane, but not necessarily the same. So it can be somewhat folded. It can be folding. It can actually be changing that angle between the front and the back halves on landing, but it cannot be rotating. It can't be coming in at an angle. So that, which again, is based on personal experience as humans and watching animals deal with the fall. Okay, and so as far as the control, okay, so that rho that I already used, apologies, is going to be the relative, the change of shape, so the difference between the orientation of the front and the back halves. We're going to use the right trivialized velocity of that rotation matrix as our control. So how is it changing its shape? And then that gives you a relationship between that value and the body angular velocity of the front and the back halves. We're going to assume again that we have some quadratic control that gives us our admissible control regions, and then a bunch of setting up. So this should look like what you pretty much would expect for a two-rigid body type problem. Key thing here, if this is your spatial angular momentum, that conservation law is used to build your control vector field. Okay, so it's in there physically, even though it's not driving the optimization. And then very quickly, and then I will stop on this. Again, something that may set some people's teeth on edge is I would advocate using a mix of right and left trivializations. So you're doing Hamiltonian system on Lie groups. And this is actually going to give you something that's within a consistent context of thinking about control from the perspective of the front half of the cat has the brain, and it's thinking about how to move relative to its current position. So I think probably nobody would be bothered by using left trivialized for the front half. But I want to use the right here. If I use left, I'd say the cat's thinking about how to change its position from its reference position rather than from its current relative shape. So I'm certainly open to being convinced that's not the right choice. Build your Hamiltonian. Now this, again, it does depend on the overall orientation, but only through its notion of what's up. So this drops to SO3 sphere, 2 copies of R3, and then you have a scalar conservation law. Super quick. If you then actually do throw in the no-twist condition, you can then reduce further. That no-twist will say you either need to have something that explicitly penalizes upside down total zero angular momentum, just do that. Okay, and so the no-twist condition says you're not allowed to do that kind of thing. Ideally, I'd like to say you can do some twisting, but not too much. So if you have the no-twist condition, then you only need to track the center axes of things. You have a further reduction you can carry out, an additional conserved scalar quantity that comes in. You can drop down to 2 copies of the 2-sphere, 2 copies of R3, 2 constraints, and that's where, here's a couple of very quick numerical simulations. Sorry not to have labels on these. So these are now, so axis of symmetry, 2 other axes. This is then telling you the position of the axis of symmetry of the rear half of the cat relative to the front half being oriented in. So when this is 1, the 2 axes are aligned, pointing in opposite directions. Here then is your perception of which direction is up. So this is upside down when this hits 1. And notice here, it doesn't quite get there perfectly. I'm having to learn a lot more boundary value problem with constraints numerics than I know right now. So these are tweaked by hand, but once this gets up to 1, then it's in the true orientation. These are then the auxiliary variables associated to this, associated to that. So now this one knows fairly large flexing. So here it's starting like this, coming up about like that, and then doing pretty much one little cycle of the hips to get two loops there. Next one, this is the arthritic. This is the middle-aged cat. It cannot comfortably flex it far, but it's still in good shape. So this is maybe the Samba kitty. So it's doing small rotations, but having to do a lot of them to complete the maneuver. So this one is taking more effort. So if total amount of movement is a big pain controller, this is probably better. If the actual moving is what's bothering you, and once you're there, it's not so bad, the previous one would be preferable. And then here again, it gets almost but not exactly to the inverted state. And then here just comparing. This is now, again, sorry not to have labels. This is the relatively flexible, and so doing large, slow loops, 2 loops. This is the not so flexible, having to do several little loops to do that switch of swinging things around. So I am definitely just really getting going with the numerics. And again, if anyone has some advice on good algorithms to use for being able to really specify, right now there's too much hand tuning of this. So that's only a couple sample simulations. I trust them about half as far as I could throw an actual cat. But let me then stop there. And thanks for listening. And one more. Whoops, we'll jump that. Happy birthday, Jair. And this is the... If you don't recognize that stack of animals, that's the worst singing quartet in the history of Western Europe. So that was my how it would sound if I tried to actually sing Happy Birthday. So I'll just say it.